contract, then what this means is that for times very, very much later than that, the relaxation time of one of these star clusters should be very nearly the same as the age of the star cluster. And that's almost all around about a Hubble time. So it's a very nice prediction from this model that all star clusters should have the same relaxation time, and that the relaxation time should be the same as their age. Now there are factors, numerical factors built in here, and when one does this, it turns out that the relaxation time should be around about a third of the age, around about a third of the Hubble time. You can find the correspondence with observational data on the star clusters given in that paper. But it also helps to understand something which has puzzled me for a very long time, from the so-called theory of the survival triangle. And one of the expositions of that was given by Ned Nostracker a while ago. What's plotted here is for each of the galactic globular clusters which were known at the time, its half-mass radius in parsec, in logarithmic scale, and its estimated mass also in logarithmic scale up here. And the idea of this survival triangle was that the star clusters are destroyed by three effects, one of which is relaxation-driven expansion and mass loss, by two-body encounters, basically. There's another mechanism which I won't talk about at all, which is the fact that when star clusters pass through the galactic disk, they are jiggled by the potential of the disk, which helps to heat them up and cause stars to escape. And finally, if the star cluster is very, very massive, here it's of the order of 10 to the 8 solar masses, then dynamical friction will tend to frick the star cluster into the galactic center. And I guess you'll hear about this in the relative coming next week. Now, okay, so here's a destruction mechanism here, destruction mechanism here, destruction mechanism here. And I always naively thought, well, you should find the star clusters in here. And I thought, well, the fact that you don't find them all over this triangle simply means that they were formed up here or something like that. But Mark gave what I think is the correct interpretation of this diagram. He thinks it's simply a different interpretation of this diagram. And the fact that a tremendous number of these clusters line up on a line of constant relaxation time, which is of the order of a Hubble time, is simply, I think, and that's his interpretation, that 2/3 of these clusters are actually still in this expanding phase in which their radii is still significantly less than their tidal radius, and therefore all of these clusters will have the same relaxation time comparable to the Hubble time. It's a different interpretation. I think it's a more correct interpretation. It doesn't apply to the 1/3 or so of the star clusters which are definitely tidal bound, but I think it was a tremendous conceptual advance. Oh yeah, before I get on to the explaining simulations, there's one thing we've got to put back in here, and that is the core radius. I already showed you the density profile of one of the models that I've been talking about, and it goes up to infinite central density. So somehow one's got to put the core radius back into this problem if you want to have a sort of comprehensive picture of star clusters, which definitely do have a core radius and a flat core. So again, I'm going to appeal to an idea of Enon's, which actually comes from a paper in 1975. And he pointed out it's a kind of counterintuitive thing, which is why it's important to try and understand it. I told you that there was this exothermic mechanism in the center of the cluster which was giving out all this energy. Now you would naively think, if you were somebody like me, that this power source is going to drive an expansion of the cluster. And that it's the amount of energy, the rate at which that energy which is coming out, which determines the rate at which that expansion takes place. And in fact, Enon showed that was thinking about the problem back to front. He said that, you know, I've got my homological model not knowing how much energy was going to be pumped out. And the model told me how much had to be pumped out by the central energy source. So it's the other way around. It's a condition of the flow of the thermal energy by the two-body interactions throughout the bulk of the model, which is determining how much that central energy source has to give out. So I call this Enon's principle. I don't know if anybody else does. The size of the core simply adjusts to produce the energy required by the cellular evolution. And Enon makes this argument if the core is too large, generally speaking, the energy generating mechanisms like binary formation are acting too slowly. They don't give enough energy out, so the core will tend to collapse, just like it did in the original core collapse. Whereas if the core is too small, it's giving out far too much energy than the rest of the, compared with what the rest of the cluster can absorb. And that tends to drive core expansion rather than cluster expansion, quenches the energy emission, and you reach an equilibrium core size, which is determined by saying that the core of the right mass is giving out exactly the amount of energy which the homological model needs. And that's what one calls balanced evolution very often nowadays. Here's an example of an energy generating mechanism. It's the energy it's a rough formula for the energy generation per unit mass given out in binary formation. It depends very, very strongly on the density, very, very strongly on the velocity dispersion, and implicitly very, very strongly on the radius of the core. And so as the core radius rises or increases or decreases, this can adjust very easily to the required amount of energy. Now I said that we would reach this balanced evolution, and it turns out that that actually does happen, but not if the cluster is too big. Because in Enon's homological models, the region around the core is nearly isothermal, and if that region is too extensive, then again it's gravithermally unstable, and this gives rise, in the presence of the central energy source, to excess expansion if the core tries to expand, and this expansion causes the cooling of the core and a runaway expansion of the core caused by the gravithermal instability again. And so you actually get a chaotic cycle of collapses and re-expansions of the core, which was discovered long ago by these two people. And so it turns out that in the equal mass systems with more than a few thousand particles, it's not possible for the core actually to reach a steady equilibrium which is giving out the right amount of energy. It's actually engaged in a chaotic kind of cycle in which on average it gives out the right amount of energy. And there's a certain amount of work, not nearly enough, on what this critical size is if you don't have stars with equal masses. All we know is that it's much larger, and we know a little bit about two-component systems. And here are gravithermal oscillations of the kind which I've just described in n-body simulations. This one is 32,000 equal masses. So what I've plotted here is the core radius as a function of time. This thing here, the decrease of the core radius down to a very small value here, is the core collapse, and subsequently one has these expansions and collapses of the core, which are the gravithermal oscillations, and it tends to be down at the bottom of these collapses that the energy is actually generated by the formation and dynamics of star clusters. Now this looks highly idealized. This is also kind of idealized. It's an n-body model of a particular star cluster which Giersch and I had studied. And so what I've shown you here is 1 gigayear after 12 gigayears in the life of this star cluster NGC 6397. So this is as honest an n-body simulation as I know how to carry out. It's got everything in this model, including primordial binary stars and so on, except stellar evolution, which is a weak process at the very end of the lifetime of one of these star clusters. And what I've plotted here are so-called the Donjon radii, but I want you to focus on the red crosses here, which are the core radius. It's a very interesting fact, I think, that the core radius is something as well observed in some of these old globular clusters. Oscillates more or less like some kind of semi-regular variable star. So sometimes you would capture it with a very, very small core, as we actually do with NEC 63, 97 presently, and sometimes it would have a much larger core, like some of its brothers do. I think I'll really move on a little bit. I've talked about some energy generating mechanisms, mainly focusing on C-body binary formation. But you don't actually need to wait for binaries to form, for binaries to start interacting, because star clusters were certainly born with primordial binary stars. Mass loss by stellar evolution, if the mass loss is sufficiently rapid, this corresponds to an unbinding of the core and is thermodynamically equivalent to a heating mechanism in the core. Even the action of the central intermediate mass black hole, although it can't give out mass, it can certainly give out energy by absorbing stars. And then time-dependent external gravitational fields also heat up star clusters. But this is not a centrally concentrated mechanism, so its effect on star clusters is a bit more complicated. But except for this issue here, and to some extent the same is true of stellar evolution, which of course occurs everywhere throughout the star cluster. Although the massive stars do most of this work tend to be concentrated near the center. By Enon's principle, the core radius is basically set by whichever one of these mechanisms is most efficient at any particular time. So what we're going to do is to take you through now the entire lifespan of, well, not exactly a globular cluster, because nobody's ever observed that, but at least simulations of my favorite globular cluster. I'll say a little bit more about M4 tomorrow, and in particular I'll say a little bit more about the simulation, which was my pride and joy for a few years until it finished last year. And I'll say a little bit about M4 itself as well, because I think it would be awfully nice if you could get up onto the roof some night, open up that telescope and show everybody M4, because it's ideally placed in the summer sky. And you can't see it from Scotland because it never gets dark at night in the middle of summer. So, Toronto is going to be ideal for this kind of thing. And if we can't get the telescope open, if somebody's got a pair of binoculars, let's go at least up on some high roof and try and see the thing. Okay, so this is an n-body simulation of the entire life cycle of M4. I'm going to show you some bits of it and also some bits of a so-called Monte Carlo simulation. I'll describe simulation less in detail tomorrow, but let's just accept that one can do this kind of thing. And what I've shown you here is the evolution of the core radius for the first 150 million years of the lifetime of this model. By the way, there's one simplification in this model, which is a simplification almost everybody does, which is that this was a single population formed at time zero at the birth of the star cluster. And it takes about 5 million years or so for the first star to start evolving, and so you see there's a wee decrease of the core radius, which is simply caused by mass degradation of the heavy masses. And then the heaviest masses start to evolve, and they turn into black holes and stuff, and they lose a lot of mass, and that mass loss causes expansion of the core. But even that mass loss diminishes in rate as time goes on, but it leaves this population of very heavy objects, at least by stellar standards, very heavy objects. And these heavy objects start to go into their own core collapse, which was only temporarily arrested before the stellar evolution kicked in. And this core collapse is what I actually call first core collapse, because I'll show you another one in a minute. So this core collapse is fundamentally the collapse of a central population of stellar mass black holes. And what happens now is what I've already shown you to some extent. There's a sequence of what I think are gravitothermal oscillations, mainly in the population of stellar mass black holes, which are trying to reach this optimal core radius in which their dynamics will be feeding the required amount of energy into the rest of the star cluster, which is revolving away and expanding above us. So I hope that from what I've explained to you, one can understand at least the first 150 million years of the evolution. Now I'm going to switch to the Monte Carlo simulation, which covers the time from birth, just off the left-hand margin here, up to 12 giga years, which I'm assuming is now. And this expansion of the core radius here is, well, the Monte Carlo model is not nearly as good for doing the gravitothermal oscillations here. It shows the expansion of the core radius, which is driven by the stellar mass black holes and by residual stellar evolution mass. Both of these mechanisms become very, very weak after about 4 or 5 giga years. And then what happens is that there's nothing else for it. The core is going to try and give up the energy required by the rest of the star cluster, so it tries to collapse. I'm treating this core in a very sort of anthropomorphic fashion, saying that it tries to collapse to satisfy the energy needs of the star cluster. It's the best language for studying what happens. As the density of the core increases, the various energy generating mechanisms which are available to it are actually becoming more and more efficient, and eventually it reaches a radius at which interactions involving the primordial bindings become active enough to supply the energy needs of the cluster as a whole. And I must say that realizing that this phase here was the onset of the energetics of the primordial bindings was a bit of a revelation to me. I'd rather assume that almost all of this evolution was driven by primordial bindings and stellar evolution massively. But I think it actually kicks in here, and here one does see gravitothermal oscillations taking place from around about 8 giga years onwards. And so I think the star cluster M4 is just at a phase of its core radius evolution at which the core radius is visible, large enough to be visible. So that's what I call second core collapse. The first core collapse is down here for the stellar mass black holes collapse, and because of a certain confusion with nomenclature, I think that where core collapses occur in environments of star clusters. But I hope I'll go in a wee bit of a rush and a bit of a demand on the thinking. You can see that even a very complicated problem like this, which has got external effects, it's got stellar evolution, it's got primordial bindings, as well as two-body relaxation, is something which one can actually try and understand qualitatively on the basis of, basically an argument. Let's just push on a little bit more. Here's the evolution of the half-mass radius of M4, and this expansion here is the expansion of N on the solar-logical model, except this is a multi-mass model. And then around about now it begins to turn around, not because of the impoverished energy generation of the core, but simply because it's beginning to meet the decreasing tidal radius out here. And this M4, I think, is one of the star clusters which is tidal bound at the present day. And the evolution here is a subtle effect of later effects of core bounces. Gravitothermal oscillations in the core. Inexorably, the half-mass radius of the star cluster decreases from now on. Here's the evolution of the total mass. The initial mass loss here is mainly stellar evolution mass loss, and after that, especially from about here onwards, It's the overflow by escape across the tidal boundary. Now, what I'm going to say about escape now that I haven't already said yesterday. I can't quite remember, but this is press ahead. We'll get there in a minute. Anyway, this will be a relief to you. This is something which you've already seen because I mentioned this yesterday and I showed this very self-same picture. Remember that star clusters are embedded in a tidal field. They're Lagrangian radii. Here, the potential well of the star cluster has saddles at the Lagrange points, and you tend to get escape of stars across these saddles. Now, this part did arise especially in discussion with Heggie that one looking at a diagram like this, one naturally thinks that this is a kind of well full of water, and it just happens to spill over the saddle here as soon as the level of the water rises too high. But in fact, it's perfectly possible because of the centrifugal and Coriolis acceleration, it's perfectly possible for stars to sit inside the star cluster forever at energies which are above the energy of this threshold. And I call these stars potential escapers because energetically they look as though they have enough energy to escape that they actually don't find their way there. And this population is quite significant. It reaches 5 or 10% of the total population, even in large star clusters like F4. And their effects are quite interesting. For one thing, they change the time scale of escape, which is no longer the relaxation time, as I've assumed so far, but varies with n and the relaxation time in a slightly more complicated fashion than that. And this is certainly true as long as the star cluster is tidally limited and not essentially isolated. A very interesting unexplored issue here is what these potential escapers look like. Remember, these are stars inside the cluster which look as though they've got more than enough kinetic energy to escape. And there are actually 2 or 3 clusters, Forza copies one of them, which have 1 or 2 stars which do seem to be moving awfully fast by comparison with any sort of standard model of the star cluster. And I've often wondered, and never actually investigated the matter much, whether these high-speed cluster members are not these potential escapers which one finds in some abundance in envelopes. And then I had this, I think, when I was talking briefly about my projects yesterday. Nobody understands these issues in the more realistic context of clusters moving on orbit with active orbits. Well, we can calculate and simulate these things, but we can't understand them. And I think the point of the project is to try and make some progress in that. One of the things which the simulations tell us is that there's a very old idea going back to Alvin King, I think, that the edge radius of the star cluster is set at the pericenter, where the tidal radius seems to shrink to its minimum, and you'd imagine that lots of stars become unbound. But you simply get recaptured again, and if you actually look at the evolving profile of star clusters moving around an oval orbit, it's almost rock steady. Is that clear, somebody? Can do it? Okay, I've said that the edge radius is almost steady to fall out of star cluster model around the elliptic orbit, as long as the eccentricity is not popping. Oh yeah, a little bit of light-hearted stuff just to round up. I've talked a little bit about escapers in the last few minutes, and I'll show you some simulations of escapers, but everybody's probably seen what happens to escapers from this star cluster, Palomar 5. And we form these beautiful with slightly longer streams emerging for several degrees on either side of the star cluster. So let me just show you a simulation again. There is a slightly tricky way of doing this. And I'll show you simulations of our tidally bound star cluster. Well, the Lagrange radius is around about the size of the frame here. So all you see is the star cluster, so the stars milling around, and it actually wobbles round and round because escapers give it a sort of back reaction, and eventually wanders off the frame until that's the end. Anybody want to see that one again? Somebody said sure. Good. Actually, the Lagrange points are rare to the right and the left here, around about the edge of the frame, but their effect on the part of the star cluster which you can see, which is mostly the star cluster that you can actually tell, is pretty trivial. So let's have a look at, let's pan out a little bit and so now the Lagrange points are within the frame here, and if you look carefully you'll see that stuff is actually spilling out in that direction, not quite right and left, but actually bottom right and upper left, because of the Coriolis acceleration which is actually modifying their trajectory. And I'll show that one again. This is a simulation of a star cluster with around about 1,000 stars, I think. So it's not huge, but it's typical of what happens in any star. One thing that you could see, I should have drawn attention to that, actually, in fact I should show it one more time, is that stars can be ejected to some considerable distance here and then find their way back into the star cluster. But usually not. And I think finally. So there's a star cluster doing the same thing, and as the stars spill out beyond the Lagrange points, they fill up these lovely tidal tails, just like around about Palomar 5. Interesting thing happens in a minute. Yeah, you see all this sudden emission of point masses. That's core collapse in that star cluster there. Because the escapers which are created by binary interaction are relatively very energetic, and they make a spectacular little firework display at about the time the core collapses and cluster.
Are there different colors, different star masses?
I don't think so. I think it's just the beautification of the star. And that now stop. That's what we store for you tomorrow morning. Numerical methods, and I think I've got to stop for the moment.
So we have coffee downstairs? Okay, coffee downstairs and then back for half an hour for the next step.
Sure. Oh, it was back in the summer.
They don't necessarily. But I think that there's some that are very tight noisy and that it isn't clear that may have past interaction that there's no
The majority. So with the ground center is that.
Well, actually, really,
I always get early and late types of
Okay,
to
so-
be honest with you. But yeah, so it's the correlation.
Early is
Earlier or later, whichever direction it goes.
Early is more like ellipticals, bigger bulges.
Right. Yeah. No, but I forget.
interaction
Yeah, I always
outside
get
the start
confused about which type of spiral is which. So but anyway, but yeah, so there's a correlation between SA and SBS. The color of the spiral is dominated by.
So, but I guess the point is, something with the actual because later type analysis. When you show the focal run,
Right.
stars,
Right.
and they have higher rates of stars.
Right. So then those would be the problem.
Exactly.
Anyway, that's my understanding, and I don't think that, it's a case of those kind of situation.
Right.
And that's also remember meeting, so I don't know if you're interested, but Alma Green and Alma Green was the initial theoretical paper, I mean, it was observational, but they presented the theory. Right, exactly. So I can look it up for you if you're interested. But then, observationally, how much we're right, who's on it,
although I'm usually
So I have two, but I don't know if it's an accent or what. So, but anyway, he did some work and there was some follow-up observation.
Can you say something about the benefits?
well,
I just, I thought I would write after it.
So the reason, the reason
all
it's
of
so
us,
right, the axis is bench star